Today we'll determine the electric field along the perpendicular bisector of a wire of infinite length with a uniformly distributed charge. So first we need to determine the electric field along a particular point on that bisector, and we exploit symmetry to simplify the problem. So what we have is a differential charge on both sides of that bisector, and we draw the electric field at this point here due to both infinitesimal charges. So given that these differential charges are at the same distance r from that point, then the differential electric field due to both of these charges is going to have the same magnitude. So these are what the vectors look like, which are of the same length and at the same angle theta from the bisector. Now applying the method of superposition in the horizontal and vertical directions. So in the horizontal direction, we have dEx is equal to the magnitude of dE sine theta. So that gives the component of this vector in this direction, and then minus dE sine theta, which gives the component of the electric field vector in this direction. So note that this theta is equal to this theta, and that's equal to this theta by symmetry. So in the horizontal direction, we have a net electric field of 0. And now in the vertical direction, if we apply the superposition principle, we have dE cosine theta, which gives the vertical component of one of these electric field vectors, and then plus dE cosine theta gives 2 dE cosine theta in the vertical direction. So the net electric field is going to be acting in the vertical direction due to symmetry. And now recall that dE was equal to 1 over 4 pi by the permittivity constant multiplied by the differential charge on the radial distance squared from that differential charge to the point we're looking at. And now substituting this differential electric field for a single differential charge into this equation, we effectively get dy is equal to 2 on 4 pi epsilon naught, and that's multiplied by dq on r squared. And of course we have cosine theta. And now we can integrate both sides of this equation. So what we get is the magnitude of the electric field, and we know it's in the vertical direction due to symmetry, and we have 1 over 2 pi epsilon naught, and we're integrating from naught to infinity. Because note that the wire is of infinite length, and we've accounted for the electric field due to the differential charges on both sides of this perpendicular bisector due to symmetry. So we're only integrating over half the length of the wire. So from the origin to the infinite length of the wire. So on this side we have minus infinity. And dq, being the differential charge, is equal to the linear charge density by dx. So what we have is lambda dx on r squared cosine theta. And now we can do a bit of geometry. So we have the distance from the origin of the wire to this point over here where we determine the electric field is y, and we denote the distance from the origin to the differential charge as x. And now we can rewrite this integral. So what we have is lambda outside the integral, because the linear charge density is constant for a uniformly distributed charge. And we're integrating from naught to infinity. And by Pythagoras, r squared is simply x squared plus y squared. So we have dx on x squared plus y squared. And cosine theta is equal to the adjacent y on r. So what we have is y over the radius, which is by Pythagoras' theorem, is root x squared plus y squared. And now let's continue our equation on this side. So what we have is lambda on 2 pi epsilon naught by the integral from naught to infinity. And we can take y outside the integral because we're integrating over x. And we have dx over x squared plus y squared to the power of 3 on 2. And now we can use trigonometric substitution. So if we let x equal y tan theta, which we can deduce from the relationship in this triangle. So tan theta is x on y. And differentiating this equation with respect to theta gives us dx is equal to y sec squared theta d theta. And now we can make our substitution. So we get lambda y on 2 pi epsilon naught by the integral from naught to infinity, and dx is y sec squared theta d theta. So we take y outside and we have sec squared theta d theta, and that's over x squared plus y squared. So x is equal to y tan theta, so we can factor out y squared, and we have tan squared theta plus 1, and we're taking this to the power of 3 on 2. And therefore by our trig identity, so recall cosine squared theta plus sine squared theta is equal to 1. And if we divide this through by cosine squared theta, we get 1 plus tan squared theta is equal to sec squared theta. So therefore this is equal to lambda by y squared on 2 pi epsilon naught by the integral from naught to infinity, and we have sec squared theta in the numerator, and we're integrating over theta, and that's divided by y squared to the 3 on 2, which would be y cubed, and that's multiplied by sec squared theta to the power of 3 on 2, so that would be sec cubed theta. And now simplifying this further, we have lambda over 2 pi epsilon naught y by the integral from naught to infinity, and sec squared theta on sec cubed theta is 1 over sec theta, which is the same thing as cosine theta, and we're integrating over theta. So one thing we may recognize, as the length of the wire goes to infinity, the angle theta goes to pi on 2. And let's really visualize that. So as you can imagine, as the length of this wire just keeps getting longer and longer, so this angle theta is going to keep increasing until this line becomes flat. So theta is going to approach pi on 2. And therefore we can rewrite this limit of integration as pi on 2 for theta. So therefore what we get is E is equal to lambda on 2 pi epsilon naught y. And evaluating this integral, we have sine theta evaluated from naught to pi on 2. And sine pi on 2 is 1. So therefore our electric field becomes the linear charge density on 2 pi epsilon naught by y. And you can notice that this is the exact result we got using Gauss's law. So if we go up to our diagram here, remember that when we used Gauss's law, we simply took a cylindrical surface with the axes along the wire, and we assumed that this surface was sufficiently away from the ends of the wire, which is the same thing as making the assumption that the length of the wire is infinite. And therefore, we had no flux going through the ends of the cylinder. And consequently, the electric field depends on the radial distance from the wire. So in this case, our radial distance is explained by this variable y. So have a look at the result using Gauss's law if this does not make sense. And I'll see you in the next video.